This video provides a summary of the tension testing procedure detailed in ASTM A370, Mechanical Testing of Steel Products. The purpose of this test is to determine the modulus of elasticity, also known as Young's modulus, yield strength, also known as yield stress, ultimate tensile strength, and percent elongation of round specimens. When performing tension tests, the following safety precautions are required: safety glasses and closed-toe shoes. Also, please note that a loud noise upon failure of the specimen is expected. The following equipment and supplies are required for conducting tension tests: a servohydraulic test system, a test specimen, a tape measure, calipers, a marker, and an extensometer. The tension test is performed to ensure that a product has the required tensile properties for its intended use. You will use the tension test results to determine the following properties: the modulus of elasticity, also known as Young's modulus, the yield stress, also known as yield strength, the ultimate tensile strength, and the percent elongation. The elastic modulus is determined at relatively small loads where the stress is proportional to the strain. As the strain increases, the material will begin to yield. Upon yielding, it will take smaller and smaller increments of stress to produce a given increment in elongation. For some materials, yielding will result in a zone where the stress will not increase with an increment in strain. This stress is determined as the yield point stress. The ultimate tensile strength is the maximum stress held by the specimen. The elongation is the specimen strain at failure, usually expressed as a percent. Some materials do not exhibit a clear yield point where the stress ceases to increase as the specimen elongates. In this case, a line is drawn parallel to the linear portion of the stress-strain curve, offset by a specified strain. The intersection between the offset line and the stress-strain curve defines the offset yield stress. The cross-sectional area of the specimen is smallest near the specimen center to ensure failure within the gauge length. Measure the length of the reduced cross-section within the specimen. Mark gauge points to create a 5-inch gauge length near the specimen center using the calipers and the marker. The purpose of the gauge marks is to determine the percent elongation after failure. Measure the diameter of the specimen at 4 locations within the gauge length using the calipers. The specimen is not perfect, and therefore minor variability in the specimen diameter is expected. The TA will secure the specimen in the servohydraulic test system while the machine is off. The TA will then affix the extensometer to the specimen. The test system will deform slightly as force is applied to the specimen. The extensometer measures the specimen deformation within a gauge length directly without the confounding effects of test system deformation. Prior to starting the test, the TA will close the door to the safety cage and secure it with a pin. The displacement rate to apply to the specimen is selected based on its geometry. ASTM A370 states that the free-running rate of crosshead displacement shall not exceed 1/16 of an inch per minute per inch of reduced section. Correspondingly, if you have a bar that has a reduced cross-section diameter of 0.5 inches and is 3 feet long, the crosshead displacement shall not exceed 1/16 per inch per minute times 36 inches, which equals 2.25 inches per minute. You will calculate the required displacement rate for your specific specimen geometry during the in-class laboratory. The TA will enter the selected displacement rate into the test system software and start the test. Observe the load versus strain curve generated by the test system software. Initially, a linear relationship between load and strain will be observed. However, as the load applied to the specimen continues to increase, the specimen will eventually yield, and a corresponding decay in the slope of the load versus strain curve will be observed. When the load response ceases to increase as the strain increases, the TA will stop the test and remove the extensometer to prevent damage. You may notice a blip in the data corresponding to when the test is paused. This is caused by relaxation of the stress within the steel while it is held at a constant strain. The TA will resume loading until failure. Observe the specimen and the load versus strain curve displayed by the test system software. The TA will remove the specimen from the machine after failure. Fit the ends of the failed specimen together and measure the distance between the gauge marks using the calipers. This measurement will be used to calculate the percent elongation at failure. In the laboratory, you will test both a steel bar and a composite bar following the procedure outlined in this video and observe the differences in properties and failure mechanisms.